little bit about him. Okay, sorry, I lost my page. Okay. Pablo Samuel Castro moved from Quito, Ecuador to Montreal to study at McGill University, where he obtained his bachelor's and then his master's and PhD on reinforcement learning. He is currently working at Google Brain as software developer while focusing on fundamental reinforcement learning research. Besides being a great researcher, Pablo is also a great musician. He does not let any opportunity pass to put music and his research together. Now, it's all yours, Dr. Castro.
Thank you. I don't know if that dialogue that I see there, sorry, is that on? I don't see it on my tablet, which is where I'm presenting.
I can see your screen. I see machine learning and creativity.
Oh, okay, sorry. Then it was, sorry, I'm connected to two different devices because I have audio. So once I get into the audio part, if you don't hear anything, let me know, because then we'll have to fix it.
Perfect.
Okay. Hello, everyone. Thank you for inviting me. I'm really honored and happy to be here in this great event. Thank you to the organizers for setting this up. My name is Pablo Samuel Castro. I work at Google in Google Brain in the Montreal office, but I actually live in Ottawa, which is where I'm talking to you from. And today I'm going to talk to you a little bit about some of my research related to machine learning and creativity. So I'm originally from Ecuador, Quito, Ecuador, in South America. That's where I grew up. But then I moved to Montreal to do my undergrad at McGill. So I did that quite a number of years ago. And after finishing my undergrad, I stayed in Montreal and I worked for this flight simulator company called CAE. That's still around. That was great. But after 3 years, I started getting the itch to go back to school. And it so happened that around that time, I randomly ran into Doina Precup, who's still a prof at McGill. I ran into her on the street and I had done my honors project with her. And so she said, why don't you come do a master's with me at McGill? And so I did. So I went back to McGill, I did my master's and then continued to do my PhD with Doina and as well with Prakash Panangaran. And so this was a time when I was doing my research at the intersection of machine learning and formal verification, which is a kind of weird intersection. And this was a time before AI was, as I like to say, before AI was cool. So it wasn't as easy to get jobs. It wasn't as well respected, this field, as it is now. So I did manage to get a postdoc position in Paris. Paris was amazing. The postdoc itself was not exactly what I was looking for. It wasn't the type of research I was interested in. And the job market just wasn't very good. And so I already had 2 young kids at this point. So I saw myself going from job to job, from postdoc to postdoc to maybe assistant professor in different cities. And so that didn't seem like the lifestyle I wanted to have at the time. So I was lucky enough to get a job offer from Google in ads. So this is a software engineer. So at the time I thought I was saying goodbye to research, and I was okay with that. I loved my job. It was really interesting. So I did some time in Google Ads in Pittsburgh, but then we decided to move back to Canada. And this is when I joined the Montreal office, initially doing back-end infrastructure for machine learning systems in Chrome. And then after that, Brain opened up in Montreal, and I was fortunate enough to be asked to join it, given that my background was exactly in this field. And that's where I am now. I've been here for almost 4 years. So my 2 main lines of research, I guess the main one is fundamental reinforcement learning. But today I'll be talking about my second line of research, which is machine learning and creativity. But just briefly on my reinforcement learning side, I'm the lead of a library that we built called Dopamine. And this is a library for doing reinforcement learning research. It's being used quite a lot by people in the community. A lot of publications are using it. I use it exclusively for my research, and the rest of the team does as well. So if you're into RL research, you should check it out. But a lot of my research is more on the theoretical side or the foundational side. So with a lot of my colleagues, we do a lot of research on what's called distributional reinforcement learning. I won't go into the details now, but it's basically replacing single numbers with distributions, and that turns out to give you some advantages. And so we're trying to understand why that is and develop better algorithms. And my main focus right now in reinforcement learning is in building state metrics for the systems that we're dealing with. So if you have an agent in one state and questioning whether it's similar to another state, how do you tell whether they're similar or not? What does this notion of similarity mean? And so we do this via these formal mathematical models called state metrics. So a lot of my work is focused on that right now. But today I will be talking to you about my other line of research, which is machine learning and creativity. And so before going into some of the work I do, I'm a musician. So I've been playing music most of my life, definitely for longer than I've been a researcher. And so music has always been a very, very important part of my life. And one thing that when I started doing this work that struck me sort of in retrospect, I mean, it's kind of obvious in retrospect, but there's a lot of structure in music when you think about it. So if you start from just the frequencies of the tones that you hear, this is where a lot of the music theory that we have in the Western world comes from, this 12-tone harmony, the relationship between the different frequencies of the pitches. Pythagoras developed this theory, and then lots was built on top of that. It's a very structured relationship that we have there. When we think about more modern music theory, like the circle of fifths or the circle of fourths that some of you may be familiar with, that's a very structured system. Or if you think about the long form compositional structure of a sonata, for instance, in a symphony, that has a very structured form, and most composers until fairly recently would follow that structure pretty rigidly. Or if you think about something more modern, like a 12-bar blues that many of you likely have heard or even played, this also has a very structured form. It's 12 bars, as the title says, but also the chords, the different chords that you use typically follow the same pattern every time. And then you can get something a bit more esoteric like 12-tone system that Schoenberg developed. And this is a lot more difficult to listen to, but it also has a very rigid structure. And so one of the things that we do as machine learning researchers is we try to develop models that can extract that structure. It's often difficult as humans to be able to do this in a scalable and fast manner. So this book that I'm showing here, Gradus ad Parnassum, this is the original textbook for counterpoint. So if any of you have studied music theory, you know that counterpoint is an essential part of what you learn. And Bach was one of the main examples of proper use of counterpoint and beautiful use of counterpoint. So for instance, one of the things that the rules that this book tells you is, for instance, if you start with a melody, as I'm going to play now, and let me know if you don't hear it. Okay, so I think you should have heard it because I heard it in my headphones. Okay, great. Okay, so Bach can start with a melody like that, and then he can use the rules of counterpoint to write a harmonization as follows. If I can get the slide to change. There you go. The sound was a little weird. I hope it was okay for you guys. But so here we can see we have 4 voices, and these are 4 independent voices. They're all moving around independently, but they're working together cohesively. And this is thanks to the rules of counterpoint that allows us to do this. So counterpoint is very nice, but it wasn't an easy thing to develop. Composers experimented with these types of harmonizations for centuries, and they try it out in churches and sort of see how people reacted to the different ideas. And eventually, after many centuries, they came up with this set of rules for what are the best practices for counterpoint, and that's what we use nowadays. So machine learning models are able to process, if we give it enough data, they're able to find these patterns in much faster ways if the algorithms are properly developed, if the models are properly developed. And so I'm part of a team at Google Brain called Magenta, and this is what we're focusing on. We're really trying to live at the intersection of music, art, machine learning, and human creativity and feedback. And so try to incorporate both the perspectives and the visions of AI researchers, as well as musicians, artists, and the users, so people that are not necessarily trained in either research or music. And so we try to be as open as we can with everything we do. So we open source all our code. We publish papers that get released freely to the world. We write blog posts, and we interact with musicians many times and artists and develop new art. So it's a really exciting space to be in, and we're really trying to leverage the power of these new machine learning models to uncover new and exciting possibilities. Okay, so why do we have such power nowadays compared to like 15 years ago. It's because of deep neural networks mostly. So deep neural networks, as some of you may already be familiar with, are essentially these stacks of layers of neurons, and they're inspired by the brain. Our brain has billions of neurons, and that's what gives us our cognitive abilities. And so deep neural networks are inspired by that, and you create these layers of neurons where you can feed in an input, for instance, the set of pixels of an image, feed it through the lower layer, and the colors and the intensity of these pixels will activate certain neurons in the lower layer. And when those neurons activate, they send a signal to the neurons in the layer above. And some of those might be activated and send signals further up. And you continue in this way until you reach the last layer. And the last layer is the output of the network. So in this example, this network this example network is being trained to classify whether there's a cat or a dog in the image. And so it'll have two neurons, and whichever at the end of the network, whichever has the highest activation, that will be the answer of the network. So in this case, it thinks it's a dog, and it got it correct. So the way, I won't go into the details of how we train it, but essentially the way it works is we give it a lot of data, ask it to answer the question, is it a cat or a dog? If it gets it right, good. If it gets it wrong, we say, no, that bad network, that was incorrect. So the network then, using differentiation, it propagates the derivatives of the error back through the network. And that's how it adjusts the strengths of the connections between the neurons. And it keeps doing this until it reduces the errors that it's getting. And so that's how we verify if a network is well trained. We evaluate the error. So again, I won't go into too many details, but that's essentially, these things are very, very powerful. For those of you that are familiar with mathematical terms, these are nonlinear function approximators, and they're very, very powerful function approximators. So we can do lots of things with them. And in Magenta, we're trying to leverage this power to use it in creative ways. So one of the papers that, the ideas that we've been using, a lot of people have been using recently, are what are known as transformer models. And this came from this paper from some colleagues. Attention is all you need. And the idea here, this model was originally developed for things like translation. So if you see at the bottom, we have a text in English, and this model is learning to translate that into German, for instance. So I won't go into the details of the network architecture, but the idea is, as its name implies, it's using attention. So if you have a sentence that you feed into the network, what the network is going to do is it's going to send signals between all the words in that input sentence and eventually come up with an encoding of the sentence. And then when it's trying to decode or produce a translation, it's going to go word by word, one word at a time. And every time it's producing a new word, it's going to be looking at the previous words that it produced, as well as the encoding of the input sentence. And so that is how it's able to do its translation. This is quite different from previous models that we were using before, where you don't have this ability to basically look at all the different parts of the sentence. You really would only look at the previous word or a summary of the past sentence. You weren't able to directly look at words in the phrase. And this is quite useful because if you look at these two examples, for instance, you're trying to translate the English phrase, the animal didn't cross the street because it was too tired. Okay, so what the word it, right? This is ambiguous because it could be, is it referring to the street or is it referring to the animal? And so here the last word is actually crucial. In the first example, the last word is tired. So for us as humans, it's clear that it is referring to animal, right? Because an animal gets tired, a street doesn't really get tired. I mean, maybe in poetry, but in this context, no. In the second example, the last word is wide. And so we typically would refer to streets, we talk about them being wide or not, whereas the animal, you don't really say wide, you might say fat or something like that. And so the model, the way it's trained, if we look at some of the layers, we can see that in the first example, when the sentence finishes with tired, it's paying more attention to the word animal than it is to the word street, and vice versa for the second example. So this is what gives these models the power that they have. They're able to really have a cohesive and long-term structure. They're able to maintain this long-term structure because they're able to directly pin attention into words that happened previously in the phrase. And so this architecture, the transformer model, was used by some colleagues to develop the music transformer. And this was trained rather than on sentences, it was trained on music. So there's this piano competition, Yamaha piano competition, where they have young virtuoso pianists compete playing classical pieces. but they're playing on a special piano called a disclavier. That's a regular grand piano, but it's also able to capture everything they play in digital format. And so that creates a really interesting data set, and that's what this model was trained on. And because of the long-term structure that transformers are able to capture, these models were able to produce really remarkable outputs. So for instance, one example is using conditional generation. So that little snippet that you just heard, let me play it again. That is, some of you may have recognized it. It's the melody from, oops, not yet. That's a melody from Chopin's Black Keys Etude. So what you can do is you can feed that little snippet, that the first thing I played, you can feed it into the model and ask the model to continue that composition. And that's what I'm going to play for you now. So that's quite impressive. I mean, if you compared this to what machine learning models were able to produce 5 years ago, it was nowhere near this. And you can see that there's a long-term structure that's maintained. That motif that we fed into the model, you could hear it throughout the piece. So this is quite remarkable. The other thing that these models can do is they can do what we call unconditional generation. So here we're not feeding it any little snippet to sort of ask it to continue that, but we're just simply saying, okay, make a new piece. And so this is one example of what it can produce. And the visualizations are showing the red vertical bar is showing what's being produced at the time, and the little arcs show what point in the previous of what it's already produced, what it's paying attention to, because this conditions what it'll produce that, after the fact. So you can see that we still have this kind of long form structure where certain motifs are repeated. And again, this was not primed with anything. We just asked the model to produce something, and this is what it was able to produce. So I'm going to stop it now just for the interest of time. So this is great. But one of the things that interests me the most is how we can incorporate these models as part of the creative process. As a musician, that's the main reason why I do this work. And so one of my first projects when I joined Brain was actually trying to think of this in the context of lyric writing. So what I did is I found this public data set of top 40 hits over the past 60 years, and I fed it into one of these transformer models for language. And then I produced this tool that we initially called Lyric AI. So I partnered with this Canadian musician. He's fairly well known here in Canada, David Usher. He used to have a really big rock band in the 90s called Moist. So I partnered with him, and we used the model that I developed to rewrite one of his previous songs. It was originally called Sparkle and Shine, so we called the new song Sparkle and Shine 2.0, and there's a video where we explain a little bit of the process. So this collaboration for me was really great, because it was a success story of a collaboration between an artist and a researcher, or an artist and a machine learning model. We were able to produce something that was quite nice. Obviously, we didn't just take all the output of the model directly and use it. What we did is he interacted with the model, and so he took some ideas directly from the model. Others he kind of modified a little bit, and other times he just used the general idea but wrote the line himself. But this is very much in the spirit of what interests me. I want these machine learning models that we develop to be tools for artists rather than trying to replace artists completely. So the model itself, I wasn't too happy with. I felt it wasn't a very good model. Because it was trained only on lyrics, it tended to do what I show here. So if you feed in the line, "I'm your big and brave and handsome Romeo," and ask it to complete that, it will produce things like this. So it just repeats the same line over and over and over again. And so if you think about it, that's not too surprising, right? Because pop lyrics repeat lines a lot. They repeat the same line over and over and over again. And so that's not terribly surprising. But the other thing that I didn't like about the model is that the vocabulary wasn't very diverse. And again, this is not too surprising because pop lyrics aren't necessarily known for their rich vocabulary or the themes that they talk about. I mean, most pop songs talk about, parties, love, that type of thing, heartbreak. So I decided, well, what if we train a model on a data set of fiction books? That definitely has a richer vocabulary and more themes. And we end up with something like this. So using the same priming first sentence. So yes, the vocabulary is richer, it's not repeating, but it no longer looks like a song lyric, right? It doesn't have this nice structure of song lyrics that you have on the left-hand side. It just kind of looks like a sentence that was chopped up at random points. And so then I thought, well, why don't we use both? They both have advantages and disadvantages. And so that's the new system that I'm working with now. It's actually using two different transformer models. The first one I call the structure transformer, and this one is trained on the lyrics dataset, but it's not trained on the lyrics directly. So what I do is I'll take, for instance, the way I originally trained it was by taking the first line of a lyric and asking the model to predict the second line. So these are the first two lines of Stairway to Heaven. And okay, that worked okay. But then what I'm doing for this model is that I'm decomposing these lines into their structure. So I'm no longer using the words themselves, but I'm extracting the first number here is the number of syllables. The other strange symbols, those are what are called part of speech. So things like nouns, verbs, adverbs, that type of thing. So for each word, what is its part of speech? And then the model is trying to produce the structure for the next line. So again, the number of syllables, the part of speech, and as well as the last phoneme syllable. So this is what we'll use for rhyming. So the last word is gold, and this is how the phonemes for gold, so that then the model can learn how to rhyme. So that's the structure model. And again, we're not training on any of the lyrics words themselves. So the model could never reproduce an existing lyric because it just never saw the words. The other model we train is called the vocabulary transformer. And this I trained on the books dataset. And the way I trained it is I'll take a dataset corpus of books. So this is a modified version of the opening of The Old Man and the Sea. And so what I would do originally is I'd split each sentence into two halves. And so I'd ask the model, if I give you the first half, predict the second half. Or if I give you the second half of the sentence, predict the first half of the next sentence. And that's how I trained the model originally. But now what I'm going to do is I'm going to combine these sentence halves with the structure of what I wanted to produce. So if I wanted the model to produce, if I give it, he wasn't old, and I wanted to produce man who fished alone, I'm not only going to give him he wasn't old, I'm going to give him he wasn't old and the structure of man who fished alone. So as you can see in this example here, I'm specifying own. So I want the phrase to finish in own. And then the model is going to try to fill in those blanks with actual English words in a way that matches the number of syllables and the part of speech of the words. And so then the way I combine these models is the user will start with a line. This is my first line. We'll decompose it into its structure, as I mentioned before. And then this structure will feed it into our structure transformer. The structure transformer will produce the structure for the next line. And then I'm going to combine my original first line with this new structure and feed that into the second vocabulary transformer. And then this will produce the second line. And so this is how the system works together. And then we can ask it to continue from then on. And it works quite nicely. So I compared the different models. So training just on books or training just on lyrics and training with the combined models. And qualitatively, you can see that the combined model works a lot better. It doesn't repeat like the lyrics one does, but it still has that nice structure of lyrics that the pure books fails to have. It also gets rhyming, some interesting rhymes like pocket, delicate, I think the strange or danger. And these are kind of old examples. We've since improved the model, and it's doing a lot better. We're actually working towards launching this publicly. So hopefully, if all goes well, within the next few weeks, you'll all be able to play with this tool and write the next top 40 hit. So we measured some statistics on these different models, and so as expected, we see that our system is able to rhyme words more, but it also repeats less than some of the other models. And it uses more unique words, which is quite interesting. So this is pretty encouraging, and it suggests that it's doing the right thing. But we're really interested now to put this in hands of artists, songwriters, and regular people to see how they use it. Okay, so that was neat, but it required a lot of engineering, required training new models from scratch. And what if you don't want, or you can't train a new model if you don't have the know-how, or if you don't have the data set, or if you don't have the compute? One thing that I'm also very interested in is whether we can use off-the-shelf models creatively. So that means I'm not going to train a new model. I'm simply going to use a model that's already there and try to use it in a creative way or incorporate it into my craft. So one way to do this is to make delightfully silly things. So I mean this in the best way possible. So that example that I played previously, if you recall, of Bach's counterpoint, how he harmonized that initial melody. Sorry about that noise. Well, that wasn't actually written by Bach, the harmonization. The original melody was written by Bach, but the harmonization was not. That was harmonized by a model that was developed by some colleagues called CocoNet. And it was published in this paper, Counterpoint by Convolution. And so that was really cool because it's able to now take any melody and harmonize it in a style that sounds very much like Bach, or sounds like counterpoint. And so some colleagues at Google, they use this model to build the Bach Google Doodle, which I hope a lot of you got to play with, I think it was 2 years ago, where you could, on Bach's birthday, you could type in any melody, and then the model would harmonize it for you. And you can still play around with it if you Google it. You can find this doodle and play around with it. It's super fun. And so this is what I mean by delightfully silly things. So with this Google Doodle, there were millions of people that played with this around the world. And what I loved about it is that it got people to interact directly with machine learning models and to interact directly with music, even if they're not musicians. And so it really had them getting interested and excited about this intersection of music and machine learning, and just thinking outside the box, thinking perhaps a bit more creatively. I think this was a fantastic use of a pre-trained model for something really great. Okay, so another way to use pre-trained models so that you don't have to train them yourself is to tweak the model outputs to satisfy your use case. So not just take the model as is and then try to do something with it, but actually take the outputs of the model and then do something different with it. So, this is a project that I published 2 years ago. And the idea here was to take two very simple models that the Magenta team had developed before I joined. The first one is called Drums RNN. What it does is you feed in a drum beat in digital format, and the model will produce a new drum beat that's based on what you gave it. And it hopefully sounds pretty good, but different. And so the way I use this is to try to create a new drum beat for a bass line that you may have written. So for instance, these notes you see here, this is a bass line that I wrote. Doesn't matter if you can't read music. I'm going to build what I call a deterministic drum beat based on this bass line. And so the way I do this is I'm going to first add a bass drum, so that's the lowest boom that you hear in drum beats, at the first beat of every bar. Okay, that's just kind of standard drum beats. And then I'm going to add a snare hit to accompany each bass note. Okay, so this is matching the rhythm of the bass line that I recorded. And then finally, I'm going to add a hi-hat every eighth for every eighth note, and this just makes it sound a little more funky. Okay, so then once I have this deterministic drum beat that, again, it will always produce the same drum beat for the same bass line. Now I'm going to feed this to this simple model, Drums RNN, and it'll produce a new drum beat that is different from what I created, but hopefully it still works. The other model I use is called Melody RNN, which is sort of similar. Here you feed in a melody to the model, and then the model will produce a new melody that tends to match its key, so the pitches that it's using, and also the density, the note density. So if I'm playing a lot of fast notes, the model will likely produce something with a lot of fast notes, but still something kind of different. Also, if I feed it something that has fewer notes and it's in a different key, the model likely will produce something in the same key, and also with fewer notes. So one thing I didn't like about this model is that it's quantized, which means that everything is subdivided at most into 16th notes. If you don't understand music, basically what that means is it sounds really robotic. So if you've ever listened to a MIDI file, you know it doesn't have sort of human aspect to it of the performance, where you can play around with the rhythm a little bit. And so I really didn't like that. Especially, I'm interested in jazz, and for jazz improvisation, sounding robotic is just not really good. So the way I use this model then, the other aspect I wanted to address here is that I wanted to see if I could use this in a live setting. So I used to do, before COVID, a lot of live shows. And using a model like this, typically there's a lag. So there's some time from when you ask it to give you an output and when it produces the output. But when you're on stage, you can't ask the drummer, okay, hold on, pause, wait, the model is thinking. Okay, now we can continue. You know, the beat is going and you have to continue with that beat. So that was one of the challenges I was trying to overcome. How can I make this work in a live setting where we can't wait around for the model forever? And no matter how fast your computer is, there's still going to be a little bit of lag. So the way I did this is I'd be improvising on my keyboard, and then I'd feed this improvisation into the melody RNN. So melody RNN would produce something. Maybe it works, maybe it doesn't, but again, it probably isn't going to be in time with the drummer that I'm playing with, because it took a couple milliseconds. So what I'll do then is I'll just remove all the rhythmic information. So I'm just going to extract the pitches of what it produced and forget about all the rhythm. So this solves the robotic rhythm problem that I was having. And also now I have these pitches ready to go to fit in the rhythm that I have. So then what happens is that as I continue my improvisation, I'll be playing some other rhythms that are really the rhythms I like to play. The system will intercept what I'm improvising, and on my case, it'll remove the notes. So it'll remove the pitch information, but maintain the rhythmic information, and then combine them. So it'll combine the pitches that the model produced with the rhythm that I'm playing. So I control the rhythm with my fingers on the keys, but the notes are controlled by the machine. So this is really like a hybrid improvisation between a machine learning model and a musician. So I'll play you, normally I do a demo of this live, but I'll just show you a video because I can't do it live because of COVID. So what I'm doing here is, first I'm going to, I'm using this tool I created. So I first set the tempo, and then I'm going to change the time signature because it was in 7/8. So I'm going to change it to 4/4, and then I'll start a click track. Okay, so then the first thing I'll do is record a bass line. Okay, so now I have a bass line, and now I'm going to create that deterministic drum beat that's directly built on the bass line. So you can see that sounds pretty groovy because it matches exactly with the bass line I'm playing. So now I ask drums RNN to produce a new beat. Not great. So it doesn't always work very well. That's kind of what makes it interesting. So one thing you can do is you can play with temperature with these models. So if you turn up the temperature very high, it's going to go further away from the rhythm you gave it. So you can see here it went really far away, and it's something really crazy. So I'm going to bring the temperature down and then ask it to produce a new beat, and this will be less wild. Okay. So this one was okay. So then my system, what it also allows you to do is record some chords. Just to kind of accompany your improvisation. So I felt the deterministic drum beat was groovier for the improvisation, so I go back to that. And now here it's just me improvising, so there's no machine learning at this point. And now here, we enter the call and response. So when you see my face, it's just me improvising, but all this is being fed into the model. And then when the robot shows up, this is the hybrid improvisation. So again, I control the rhythm with my fingers on the keys, and the robot controls the notes. So right now it's just me. So you see I'm hitting the same key, but the pitches are changing, and that's sort of the hybrid improvisation. And so this was quite interesting. I used this live a couple times. I performed with it, and it was really challenging because I'm used to, moving my fingers in a certain way and hearing certain pitches, but now I'm moving my fingers in that way and I hear different pitches, different notes. And so that was really challenging and kind of jarring. And so it really changed the way I thought about improvisation, which is really one of the reasons why I'm interested in this stuff is to push artists and musicians out of their comfort zone, because if they're well trained enough, they can navigate those uncomfortable zones and maybe come up with new ideas. Okay, so another area that I'm exploring is combining different models in different generative models in new and creative ways. So one of the models I used is what's called a GAN, a generative adversarial net. I won't go into too much details, but the idea is you, again, train on a huge data set. And what you're trying to train the model to do is to generate images that look like they came from this data set. So that initially the model will produce something that just kind of looks like noise, but you're also training a different model that's called the discriminator. And what this discriminator is trying to do is it's going to look at the output that the model produced, and it's going to say, compare it with something that, sorry, it will sometimes get something the model produced and sometimes get something from the real data set, and it has to figure out which one is real and which one is fake. Right? Real being that it came from the real data set. So in this case, it's super easy because the model produced just noise, so the discriminator will have an easy time. But the generator, they're playing this game. The generator is trying to fool the discriminator, and the discriminator is trying to not get fooled by the generator. And so by training the two of them together, they both get better, and better. And so initially, the generator will start getting a little better and start producing things that look more like faces. The discriminator has a harder time distinguishing them, but can still do okay. And as they continue progressing, the generator gets better and better, as well as the discriminator. And you keep progressing like this, and the images just keep getting more and more realistic. And so Ian Goodfellow, who's the original author of the first GAN paper that introduced GANs, he had this tweet a couple of years ago, where you can see the clear progression of the realism of these images. And it's not just trained on faces, you can train them on landscapes and all sorts of things. There's this website that's really weird. It's called This Person Does Not Exist, and those are all automatically generated faces. They don't exist, but they look super realistic. Okay, so one of these GAN models, there's a bunch of research going on in GANs. One of them that was published 2 years ago, it produced this model called Big GAN, and this was a conditional GAN. And what that means is that it's able to generate images from 1,000 different categories. So if you say generate a hamburger, it'll generate this hamburger that looks like that, or generate monarch butterfly, and it'll generate that. And so one of the nice things about this model is that it has what's called a latent space. So you can think of this as a ball of sand. And if you navigate within that latent space, you can create these smooth interpolations between different images. And so I use that in this project that I published last month. The way I use this is that I take an audio file and extract its spectrogram, which you see at the top. And then from this spectrogram, I look at how the frequencies vary. And so from that, I can extract this sort of 1D signal that you see in the middle row. And then I have an algorithm to find the peaks and valleys. And so in each of those peaks and valleys, I'm going to pick a different category that the Big GAN can produce. And then I'm going to create this sort of smooth interpolation between categories using this 1D signal. And so I'll show you, this is using, so the audio file I used is actually a melody that was produced by the music transformer, which I presented earlier. And then I fed it through my system. And so the video was automatically generated by my system using the Big GAN. So again, I didn't train any model. I just kind of took these pre-trained models and sort of combined them in these new ways. So I called this piece Latent Voyage, and I specifically picked categories that had things related to voyage, you know, like balloons, airplanes, boats. So you can see the video sort of matches how the audio moves, and it creates this really nice thing. So if you check out my website, I have a blog post on this, and you can see more examples and read more detail about that paper. Just move to the next slide. Okay, so another thing that I was exploring with this is creating sort of a narrative. So I wrote this fictional story about this fictional character called Gandhi, and I picked categories to kind of match what I was saying in the story.
This is the story of Gandhi. Gandhi started as a ball of cells and was then born in a hospital. No, he was not brought by a stork. As a child, he grew up in a farm, was afraid of sharks, but loved his puppy. He always wanted to see an axolotl. Like any Canadian, he grew up playing hockey in the winter and tennis in the summer. As a teenager, he liked listening to music and doing mountain biking. He also got.
So anyway, I won't play the whole thing for lack of time, but you can check it out on my website. But that's a kind of interesting idea to, you know, try to automatically generate these videos that are sort of weird and cool to match a story that you wrote. Okay. And then finally, another idea that I've been exploring is actually jamming with these machine learning models. And here, once again, I'm using this music transformer, which I find a really compelling model. And so I've done this a little bit. So what I'll do is I'll ask the model to generate something. So I don't know what it's going to generate. And I have one of these Disclavier pianos that I mentioned previously. I have one at home. And what's cool about that is that you can send MIDI to the piano and the keys move on their own. So you can kind of really have like a ghost playing next to you. And so I'll ask Music Transformer to generate a melody, feed it through my piano, and then I just kind of have to improvise to what I see on the keys on the spot. And that's what I'll show you here. So I have a few other videos of that on my Twitter, if you follow me on Twitter. Okay, so just to summarize, there are so many models that are being produced by the research community and the creative community that it's really endless the number of things you can do with them, and it's really at this intersection of AI, creativity, and art that I'm really excited about, because there's so much potential there. But one thing that is very important for me, and that I always try to emphasize when I give these talks, is that I think that the right way to think about these new tools and these new models is as tools for musicians or the lay person. I really don't want to be working on things that can be used as replacements to musicians or artists. For me, it's really important that the musician or the artist is always in charge, and these things are kind of like tools. So one way I like to think about it is, back in the 60s or 70s, if you were a musician, you wanted to record an album. If you wanted it to sound good, you had no choice but to hire a sound engineer and go to a recording studio. And it was expensive enough that you only really got to do that if you had a record label behind you. Well, nowadays we have things like Pro Tools and Ableton that anybody can do it in their basement. And Jacob Collier, he did that in his basement, and he won a Grammy with that. So those types of tools, they didn't replace sound engineers or recording studios. They're still around, and they're still doing pretty well. But it did enable more people to get into the space and explore things in a way that isn't as prohibitive for everyone else. It doesn't require you to be signed to a record label. So that's the way I like to think about these tools. I'm hopeful that they can stimulate new forms of art, new forms of creativity, without reducing the livelihood of artists and musicians that have a hard time making a living nowadays. So I hope these ideas stimulate you and encourage you to get into this field and start playing around. And once again, thanks to the organizers for inviting me. This was great, and you can follow me on Twitter or check out my website for more details. And I think we still have some time, so happy to take questions.
Hi, Pablo.
Hi.
Yeah. So it's been really interesting, and I'm also a musician. I've been playing piano since I was 6 years old, and I'm still playing nowadays. And I have a question. And so you played so in that video you played Chameleon by Herbie Hancock.
Yep.
And then so what your app does so you were improvising over it, and and then before that you showed that it can replicate some rhythm. And is that what does that do? Like, does that help when you're trying to come up with like different motifs?
No, not really. So it's hard to know, like, when I'm building this stuff, how it's like, whether it's going to be useful at all or how it's going to be useful. Like, I've used it a bunch of times, and it's been more of a challenge than but that's why I wanted to do it. So I mean, I've been playing piano all my life, so I know how to improvise, I know how to solo, I know how to get in the pocket when I'm performing live. And with this thing, it's sort of pushing me out of that pocket. So it didn't necessarily, at least not so far, it hasn't produced something that's like, oh, that's a neat line. Also because it's improvisation, you know, it's hard to, you're sort of in this transient space where you're coming up with things on the spot and they sort of leave. You know, they don't, at least for me, they don't stay in my head. They're just things that I come up with on the spot. But what it did do for me is that it really, you know, when you learn how to improvise in jazz, especially, you often learn, you transcribe artists' solos, and you learn certain patterns, you memorize them. And so it's almost like you go into autopilot. So there's certain patterns that I can do, and I don't have to think about it anymore. It's like, okay, I'm going to do this line, and I know how it's going to sound. And so it's like I tell my fingers, okay, go. And then while they're doing that, I can think of what's the next thing I'm going to do. But when I'm using the system, I can't rely on that, because if I do that pattern, the notes that are being injected by my system are different than what I'm expecting. So I have to really be present for every note that I'm playing. And there's like Lee Konitz, he talked about this a lot, about like, you know, being present for every note. And that's something that I haven't done enough of. And so this system really is forcing me to think in that way as an improviser. And so that's been, like, for me, one of the successes of that project.
Awesome.
No, thanks for the question.
Does anyone else have a question?
Maybe I have one small question.
Mm-hmm.
Yeah. So I was just wondering, how do you train models to maybe capture a composer style, a unique composer style like Chopin or somebody else, another artist?
Yeah, so it's challenging in large part because of data. So basically, you'd want to have a lot of data just on that composer. It also depends on how complex the data set is, right? So not to say that Bach chorales aren't complex, but they're quite structured, they're short. And so the CocoNet model that I mentioned that was used to make the Bach Google Doodle, that was trained on Bach chorales. And so Bach chorales are I don't know, they're like 8 measures long. They're all 4 voices. So the voices are all in the same range, and they're all sort of following the rules of counterpoint. So it's a lot more structured. And so training a model on that is somewhat easier. I mean, it wasn't easy, but it's easier in the sense that than I think it would be training something on Chopin, because Chopin has really long pieces, right?
Yeah.
And they're kind of all over the place. Like there's slow pieces, there's fast pieces, the different keys. There's, you know, the rhythm. Like Bach tends to not use things like quintuplets or things like that, whereas Chopin uses that all the time, and he uses, you know, triplets on top of 8th notes, and you know, that type of thing makes all of these make the music more complex, also more beautiful, but it's more difficult for a model to sort of learn all those patterns. The piano data set that they used for Music Transformer, that was virtuoso pianos, so that the pieces they tend to play are things like by Chopin or Liszt or Beethoven. So the music tends to follow those composers a lot. One thing that some people do is they'll train a model on large data set, like the music data set that I mentioned, but then they do what's called fine tune. So they have the model that's able to produce sort of from this whole data set, but then they can fine tune it by then sort of refining the weights on a specific composer. That sometimes works, sometimes not as well. Again, a big part of it is how good your data is.
Yeah. Okay. Maybe one last question. What would you say would be like a beginner project for somebody that is interested in AI and music, so to combine both worlds?
Yeah, I think, I mean, the one thing I tell a lot of people, not just that are interested in the space, but in general interested in machine learning, is one of the great things about the time we live in right now is that we have things like GitHub and an archive, you know, where all the papers are easy, and the internet, obviously, all the papers are easily accessible. All the code is easily accessible. Now you have things like Google Colab, where you have access to a GPU for free. So I don't know if you know that, but if you go to Google
Collaboratory.
Collaboratory, you can change your runtime to be a GPU. So you can train models already, have access to these fancy hardware to train GPUs. And sometimes you can even have access to TPUs, which can be faster. And so what I would suggest is find a project that you really like, that that really interested you, that was published recently. Likely it has code out there. So download that code, train it on a Colab, or if you have your own GPU, train it there. And first thing, just train it. Okay. And now you produce some outputs, and now say, okay, what if I change this thing? And maybe from the pre-trained model, or maybe you train a new model on a different data set. And every time, like just that, like I'm going to train on a new data set, it sounds easy to say, it's really hard, because the input data set has to be in the right format. So a lot of you hear about these machine learning models, and you just see the fancy thing and the flashy thing at the end. There was a lot of hard work that went to get to that point, starting from curating the data set. So the lyrics example, for instance, the lyrics data set, when I first started with that, I just downloaded the lyrics and trained it. And the model first was producing a lot of swear words, which I didn't want. It turned out that a big part of the data set was hip hop, which does use a lot of swear words. So then I had to curate that and say, okay, I'm going to remove hip hop, just because, I mean, I love hip hop, but I don't want this model to be swearing at people. And so, that's the type of thing that it's difficult to really understand how difficult it is until you get your sort of hands dirty and start playing with it. And when you do that, you start learning more and realizing things. Oh, actually, why didn't they do this here? And so then, maybe you reach out to the authors and say, hey, I tried this new idea on your model, it didn't quite work. Do you know why? Maybe they'll say, oh yeah, you have to do this thing, and then cool, you have your answer solved. Or they might say, you know what? We didn't realize that. That's kind of interesting. Maybe a research collaboration starts there. So really, I think the best way to start is to find something that's out there and get your hands dirty. I wouldn't suggest starting from scratch, because as I said, it takes a lot of work to get there, a lot of experience. So it's better to sort of stand on the shoulders of people that have already done that work for you, and then start tweaking. And then eventually you'll end up building your own thing from scratch. But I think to start off, it's good to start with something that's already working.
That's good to know. Thank you.
Anyone else has a question? No?
Maybe one last question.
Yeah, go for it.
Okay. All right. So I know you showed a lot of examples, and then I'm just trying to formulate. So are you saying that with what you're doing so far, would you be able, for example, to like you mentioned Bach chorales, would you be able, for example, to extract like the SATB, or for example in the Schoenberg work you can extract the tone rows, right? Would you be able to do that? Or would it require a lot of models, a lot of pieces and excerpts to do it?
What do you mean by extract? Do you mean like have the model like write out the soprano line?
Kind of thing, like trying, for example, in the Schoenberg work. I know a Schoenberg work could be much more complex because it's a piano work, but but would it be able to like find a tone row? So like the
you mean like the model? You ask the model what's the tone row of this piece, and it'll show you.
Mm-hmm.
No, so I mean maybe you could, but the model hasn't been trained to do that. So for instance the coconut, the counterpoint thing, right? So as I said, it sounds like Bach and it sounds like counterpoint, but it actually violates the counterpoint rules a lot in a way that Bach would never have, unless he knew what he was doing. So if he violated that rule, it was for a reason. The model's doing a best effort. It's really just doing statistics, pattern recognition.
Okay.
And so it doesn't know at a high level, like it's not learning these rules, and it's not learning. I mean, the soprano, alto, tenor, and bass are split up into separate MIDI tracks. So the model does know that, but that's just because we've given it the data as it is. If we were to give the soprano, alto, tenor, and bass in one MIDI track, the model would not really be able to sort of figure out which one's a soprano, unless you figured out a way to train it, and then maybe it could do that pretty well.
Okay.
Again, it depends on what your data set is, like what your inputs are, what you're asking the model to do, and how you're training it. So that model, the way the coconut model was trained is you take all the Bach chorales and they remove notes randomly, and they ask the model, fill in those notes. And so that's how the model was trained to do that, because it knows how to fill in. So you can say, I'm going to remove the whole soprano part. Now regenerate the soprano part based on the alto, tenor, and bass. And so the model learns how to do that. So then for the doodle, we could feed in, I think they fed in like whatever you typed in was the soprano line, and then the model was asked to fill in the alto, tenor, and bass.
Okay, yeah, interesting. Thank you.
Okay, so I think that's gonna be all. Thank you very much, Dr. Castro. It was amazing.
Thank you.
It was
Thank you
very
for inviting me.
inspiring too for all the musicians here. So yeah, thank you.
Thanks for inviting me.
Thank you. For all the participants,